Great. Thanks for having me, and thanks for that nice intro, Mile. I'll share my screen. Okay. So I'm excited to be with you and to talk with you about the nonlinear and heterogeneous effects of parental income on children's educational attainment. This is a project that I worked on in a postdoc last year at UCLA with my co-author, Jenny Brand. And we're still making changes and tweaks, so I'm totally happy to hear. We would actually love to hear feedback and ideas and what you think is working and what you think you'd like to see different. And you can feel free to interrupt or raise hand, however you do that here. I'm happy to answer questions along the way as there's clarifying things. So I want to start with a bit of motivation for how Jenny and I are approaching this problem. This is a picture that some of you may recognize. That's a picture of how computing looked in the 1950s. And so if you look at this, you can see sort of what's happening here. This woman in the front is feeding these paper punch cards in the machine. And that machine is like then doing the calculations and spitting back the results. So in the 1950s, there was a lot of excitement about what computing could do for us, but it was really quite basic. And you see this was a really laborious process. And so it was pretty limited. If we jump ahead to the 1980s, we get into the era of personal computers where folks could have a lot of that power compressed right into their own personal workspace. And if we jump to today, Apple in this picture has produced computers that are more powerful and smaller than any of those that existed before. And so today your computer can do a lot of things that those computers operating on the punch cards could never have done. And it's sort of all at your fingertips, and there's a lot of possibilities. And in fact, technology is also changing the way that we interact with our computers. So many of you have followed the news about ChatGPT. So just for fun, I asked them, can you write a poem about the Institute for Analytical Sociology at Linköping University? And it produces one. Deep within the halls of Linköping, a beacon of science shines. The Institute for Analytical Sociology, a place where reason refines. The mysteries of society are peeled back layer by layer, using methods both old and new to understand and prepare. It's a little dark there with the prepare. I don't know what it's preparing for, but anyhow, it goes on and on. So if we think about how computing was back in the 50s to how computing was today, there's been just this sea change of change, where now we have lots of potential possibilities for working with our computers that were really impossible decades ago. Given that backdrop about the advances in computing since the 1960s, I'd like to think a bit about how has quantitative social science changed over this same period. So if we go back to the 60s, here's a famous figure from the Blau and Duncan Process of Stratification book. And what this figure is showing is really a regression model. So we see at the right, there's an outcome, occupation in 1962, which is some score. And that outcome is a function of a bunch of inputs that all have coefficients, 0.753, 0.394, 0.115. And when you look at this model, effectively, this is just linear regression. And this is familiar to us because if you looked at stratification research today, often you'll see things like this. So here I'm picking on my own example. My outcome here is college enrollment by age 20, and we have a bunch of predictors. And we have one column, which is a regression model. This is a logistic regression model, where the left column predicts college enrollment using family income as the only predictor. And the right column adds a bunch of control variables for race, parents' education, and family wealth. And you can see many papers that follow a common strategy where they focus on that coefficient at the left, and then they see how much that coefficient on log family income declines once you adjust for the other variables in the model. And this is how much quantitative social science proceeds today, and especially, I think, much research in stratification. And we've learned a lot this way, but I think we should ask the question, given changes in computing from the 1950s to today, perhaps there are things we could be doing computationally that give us better insights and new knowledge above and beyond the kinds of things that Blau and Duncan were able to do back in the 60s. So this leads to the question, why have regressions stuck around? There I think several good reasons why regressions, in fact, have stuck around. So one reason is that we actually have learned a ton that way. Social science has produced lots of knowledge over the past few decades. And in some sense, when you have a tool that's working, it's hard to move on from that tool. Second, we can really interpret regressions. Like, we understand the math behind them, and it's easy to know what's going on with all those coefficients. And then third, we have small sample sizes. So I'm now in a college with computer science. And when you talk with computer scientists about what a small or large sample size is, they're thinking often on like orders of magnitude larger sample sizes than what we have available to us in social science. So like hundreds of thousands of observations instead of thousands or perhaps tens of thousands of observations. And when we have small sample sizes, possibly a regression is actually a pretty good tool because it's a parsimonious model that can be learned well in that small sample size. But despite these reasons to know why regression might have stuck around, both Jenny and I in our research plans are very interested in this question of how might we move on from regression? Because there are all kinds of new tools available, and it feels like we could gain a lot of knowledge in social science if we set down the regression table and moved on to methods that are perhaps more complicated than those that are most familiar to us. And so that kind of motivates what we both are doing in this paper and in our other work. So I have a quick general thought about how might we move on from regression, and then I'm going to spend the rest of the talk today talking about one specific example where we're moving on from regression to study the effect of family income. So general thought is that this is a figure from my paper with Rebecca Johnson and Brandon Stewart. What is your estimand? Defining the target quantity connects statistical evidence to theory. And in this paper, we argue that quantitative social science could make greater advances if we were clear about several steps linking our theories to our evidence. And in particular, we argue that folks should first define what we call a theoretical estimand, which is some aggregation over units in a target population of some factual or counterfactual quantity defined for each unit in that population. And we argue that setting the theoretical estimand makes it really clear how your target quantity speaks to your theory or general goal. Then we argue that once you've set that goal, it becomes clear how to use causal assumptions, as in directed acyclic graphs, to link that theoretical estimand to an empirical estimand that could be learned in observable data. And then finally, we think machine learning and all the computational capabilities available today really jump in this last step, where you're learning a quantity that involves observable random variables. And you need an estimation strategy to learn that when your sample size is limited. So I just wanted to throw this up here as like kind of the big think framework in which Jenny and I are both operating. So if this is new to you and you are like curious about how we're thinking about the world, I think this is the paper to which I would point you to learn more. But today we're going to focus on a specific example within this framework. So I'm going to tell you a bit about our data, a bit about our theory and hypotheses, how we think about causal inference in this setting. And then after we've done all that setup, then I'll get to some estimation, which involves a machine learning strategy, results, and then discussion about what we've learned. Yes, we got a hand.
Hi, and just a quick clarification question. So you mentioned, moving away from regression. So just want to ask a clarification question with regards to what exactly in regression, which is the problem. And implicitly, my question, is it really linearity that is the problem and not, like regressing Y on a set of X variables? So could you just expand a little bit on that? Thank you. Oh,
yeah, thank you for asking. So this is another fun thing, hanging out with social scientists and more computer science inclined folks, is that for some people, regression means like ordinary least squares or logistic regression, like some kind of linear predictor that's a linear additive function of the inputs. And that's the sense we're using it here. I do think there's a more general sense of regression, meaning like any function to predict an outcome given the inputs.
Exactly.
And we're actually gonna stay within regression in that sort of big regression framework.
Yeah. Okay, good. That's what was my question sort of implicitly trying to allude to. Thank you.
Yes, thanks for asking. Shall we? Okay, we'll go on to the data. So we're going to work with the National Longitudinal Survey of Youth 1997 cohort. So these kids, I'm sure you've seen this a zillion times, so I'll go sort of quick. They were ages 12 to 17 in 1997, and this is a national sample of US kids in that age range. Our treatment variable is going to be their family income in 1997. So for some kids, this treatment is experienced at age 12. For some, it's at age 17. For some, it's at age 15. But for all of them, it's at 1997. And the reason for that is so that it's all measured in the exact same way that the question was asked in 1997. Our outcome is going to be whether the child enrolled in college by age 20. So currently we require them to report college enrollment between age 19.0 and 20.0. So as we have it operationalized now, this is a very specific definition of college enrollment. And then we are actually going to consider only 3 possible confounding variables. And this may surprise you, but it's actually going to become quite difficult with only 3 variables. So we're going to do machine learning in a context where there's actually very few predictors that we are working with. So our confounders are family wealth measured in 1997, race, and parents' education. And here we've recoded parents' education into the categories that we think matter for confounding in this case. And in particular, we think that when your parents completed college, they have some cultural capital or know-how that will help them navigate the higher education system with their kids. And so we've categorized into neither parent finished college, one finished college, or both finished college. And our sample sizes are there at the bottom. So we're going to be working with about 5,000 cases, which, as I said before, is that big or is it small? Kind of depends on what your reference frame is there. Okay, so our theory. So Jenny and I approach the world with a fundamental belief that the world is heterogeneous. And this is a belief that's shared through a lot of causal inference research today, where we believe that when you have a treatment, that treatment might lead to an effect, and that effect we'll assume by default is different for every person in the population. And this default assumption is quite different from the default assumption in like ordinary least squares, where you might assume by default that the same beta applies to all the people in the population. And we think adopting this heterogeneous worldview is really helpful for answering sociological questions and building theory. And we also just think it's how the world works. But the cost is going to be that, like, statistically, things are, of course, much more difficult when you're going to believe that every person has their own effect instead of one beta that applies to everyone. So for us, the question is not whether college enrollment is responsive to income, but rather for whom is college enrollment responsive to income. And so we have a few hypotheses about this for whom question. So first off, we might think that the effect would be biggest among those with low income or wealth. So if you don't have very much income, then a given nudge to increase your income may lead to a bigger payoff in terms of going to college than if you have lots of income. That little nudge to income really doesn't make that much difference, we think. Our second hypothesis involves cultural capital. So we believe it's possible that those whose parents do not hold BAs would benefit more from a nudge to income than those whose parents do hold BAs. And our reasoning for this would be that if your parents went to college, then you have access to lots of cultural capital, and you will find a way to navigate the higher education system, even if you yourself don't have a lot of income lying around. Meanwhile, if your parents didn't go to college, then like every little bit helps. And so perhaps in this subgroup, financial capital is really effective. Now, this need not be the only way that cultural and financial capital operate together. So we can also make the opposite hypothesis, which is that the effect of income would be greatest among those whose parents actually hold BA degrees. And in this case, we would be theorizing that the parents with BA degrees possess cultural capital in the form of knowledge about how to effectively navigate that higher educational system and convert financial capital into higher education opportunities. So you could think that those whose parents don't know how the higher education system works are not particularly well prepared to use income in a way that advances their kids' education. So this is the opposite of hypothesis 2A. Any questions about the theory slide? Okay, we will keep going. So these theories invoke causal effects, and they invoke causal effects that vary across subpopulations. So we're not talking about whether income predicts college enrollment. We really do mean, like, for a given person, if they counterfactually had a different income value, would they have enrolled in college in that case? And so for that reason, we're going to draw a lot on the standard ways that causal inference is approached in statistics and social science and also biostats. So perhaps the most canonical example is this case where we have causal inference for a randomized controlled trial where we're testing the effect of a drug versus a placebo. So here we have a potential outcomes table where each row corresponds to a person. And here I've noted the factual treatment that each person received. So person one received the placebo, and then we get to see their outcome, like their heart rate or their cholesterol or whether they survived under that placebo condition. So I'm using a filled in circle to indicate that we got to observe the potential outcome under the placebo. And we didn't get to observe the potential outcome under the drug because this person got the placebo. We didn't get to see what would have happened under the drug. And this is challenging because the causal effect for person one is the difference between these two potential outcomes. So it's whether person one, like the heart rate person one would have realized if they got the drug minus if they got the placebo. And we just don't get to see that drug outcome. And this is true for all the cases. So when we look at the average causal effect, the average difference between this column and this column in this table, we have the problem that only 50% of the relevant potential outcomes are observed. Okay, we all questions on definition of potential outcomes. We're good. Okay, so this is like extremely well studied, this case where this binary treatment. So now let's move to a case where the treatment takes the value of $10,000, $20,000, $30,000, $40,000, $50,000. So now we have a potential outcome that is in many ways the same, but is also a bit different. So it's the same in that for each person, we get to observe one of the potential outcomes. So person one had a family income of $30,000, and we see whether they enrolled in college in that case. But it's different in that we no longer see 50% of the potential outcomes, but rather we see this little tiny fraction of all the potential outcomes that could have been observed. And in fact, if you think of income as a continuous variable, then this gets much worse because now there's an infinite set of treatment conditions, and thus for each person, an infinite set of potential outcomes, of which we see approximately 0 of them. So in many ways, when we move from a binary treatment to a continuous treatment, the missing data problem that underlies causal inference just explodes in complexity. And for this reason, we're going to have to rely on some kind of modeling assumptions to share information across treatment values that are nearby to one another. Okay, and I'm going to put little tags here whenever I do mention something that's like statsy from causal inference. So here I've assumed the consistency assumption, which is that the observed outcome y equals the potential outcome y under the factual treatment value a. So that just means that for someone who made $30,000, they have an outcome under $30,000, and that potential outcome is well defined, and it's the one that we got to see. So important causal assumption that got sort of slipped in there. So given the potential outcomes table, we then need to make some assumptions in order to learn about these unobserved outcomes given our observed outcomes. And the key assumption we have to make here is exchangeability. This is a nice paper that introduces using directed acyclic graphs for this assumption. And so in our case, we're going to assume that family income affects whether you enroll in college. And we have these measured confounding variables that affect whether they affect your family income, and they also affect whether you enroll in college. And we're going to assume that once you condition on these variables over here at the left, you've blocked all backdoor paths. And within subsets of those variables, the association between family income and college enrollment equals the causal effect of family income on college enrollment. So of course, this is a heroic assumption. We think it's a somewhat credible assumption, but it is a leap and it's sure to hold imperfectly. You might credibly worry about some unobserved confounders that perhaps would affect your family income and affect whether you enroll in college. And those would like totally be valid concerns. And in many ways, this is the same kind of concern that applies regardless of whether the treatment is binary or the treatment is continuous. We would argue, I'm going to come back here for a second, that while confounding from unobserved confounders is an important concern, it is actually perhaps not the most important concern when the treatment is continuous, because we have actually discovered that we are much more concerned about another problem, which relates to positivity and extrapolation. So if we move on to that other problem, we're calling this the extrapolation problem. And so this is the problem that within a population subgroup, many of the treatment values are simply unobserved. So to motivate this, let's consider a hypothetical case where we have two subpopulations. We have those for whom neither parent completed college and those for whom both parents completed college. And in some sense, you could say there's extreme confounding by this variable here, because among those in the blue subgroup, their incomes are entirely low, and among those in the gray subgroup, their incomes are entirely high. So now you might think like, well, what could we do? We maybe want to fit a regression model of some sort that will predict the family income that the blue group would have realized if their income was high, and that the gray group would have realized if their income was low. But here we have a problem, because like you could extend these lines, assuming an interaction between the groups that is linear, or you could assume that these are parallel lines that are nonlinear, and there's no evidence in the data to tell you whether you should prefer this extension or this extension. And so in general, there's a difficulty here whenever you want to make a claim about a counterfactual treatment value that just like is far away from the values observed in a subgroup. And so our response to this concern is that we are not going to extrapolate. We're going to only visualize the middle 90% of the observed treatments within any particular group. And we're going to only visualize if the number of observations contributing to a line in our plot is at least 25. And this we actually find is a pretty big restriction. So we end up having trouble making claims about, say, kids whose parents didn't complete college under a counterfactual where they had really high incomes. Because this is not just a contrived example. So here's actually the treatment distribution in our sample along the x-axis for these three subgroups defined by parents' education. And we see that, for example, when neither parent finished college, it's very unusual for us to see a family income greater than $150,000. Whereas when both parents finished college, a huge portion of the distribution is in that treatment range. So we think that while folks often think about confounding, in cases where we're looking at stratification processes, income stratification in particular can be so severe that you really perhaps don't want to think about it in terms of like adjusting in an additive sense within a regression model, but rather think about, if I looked at this subgroup, or is there anybody near the income value that I want to counterfactually learn about? Okay, question.
Thank you, Ian. So do you apply this restriction on the full joint distribution, so including the three confounders, or is it just looking at the treated distribution?
Yeah, that's a great question. So we apply the restriction on whatever we are visualizing in the plot. So in general, I'll get to this again in a minute. You could imagine looking within each subgroup defined by the confounders, or looking within one subgroup adjusting for the others.
Yeah.
And that the second thing is what we're going to do. Because if we look within each strata, we lose like everybody.
Right. But then the problem is that you wouldn't actually have the confounder information kicking in, right? So you end up having a biased subpopulation because they are, right? This is what I mean.
Yeah, let's come back to this in a minute, because at the end of the day, we have to assume some limits to the interactions that are present in order to make progress. So effectively, like here, if you're willing to make this assumption, you can proceed, and we're going to make like a slightly weaker version of this assumption.
Okay, fair
enough. Yes, there was another one.
Yeah, just to try to link that with all the literatures, or is that close to problems in matching, for instance, when you want to match two people and you can only match one because the other is not similar enough?
Yes. Yeah. So matching is hard because we have like now many treatment values instead of just two. But if you imagine you had one case over here where neither parent finished college and you want to know about their counterfactual up here, you might want to match them to someone who had that family income but looks like them, and there's going to be nobody like that. So if we did like a caliper kind of matching thing, you would just drop everybody here. Okay, continuing on with the roadmap. Okay, so what motivated us at the beginning was this question: how might we move on from regression? And so now that we've set up sort of our theory and our data, I now can get into a little more like specifically how might we move on from regression and how are we going to make some kind of additive assumptions while also allowing things to be interactive. So when we think about adjusting, one really nice way to think about adjusting is to think about just taking subpopulations defined by all the variables. So you can think of this like a really big crosstab where you just like interact everything and look at who's there. And so here I've looked in this plot just at those who identify as Black. So we've subset along race. And then each column is a subgroup defined by parents' education, and each row is a subgroup defined by family wealth. And effectively, we're going to look at the interaction of all these variables. And so if you do that, here are the data. So people are taking the value 1 along the top if they enrolled in college, 0 if they did not enroll in college. And you might think, well, we want to be fully interactive. We want to avoid extrapolation in its extreme and just like be really true to these principles we believe. And so maybe we then fit a model separately within each subset of the population. So in this case, these are all logistic regression models where family income is entered as log family income. And you can see that this is kind of nice in some ways because you get to see that the curves may be different. So like maybe there's a really steep group slope in this group, a flatter slope in this group, but you also start to get wonky things that we don't believe, like the idea that college enrollment declines with family income among those where both parents finished college and they have middle wealth. And then you also have really wonky things where when you look at it, like no one really would draw conclusions about how family income affects college enrollment among Black families where both parents finished college and yet they have low wealth, because that cell of the population has only 2 cases. And so this is a cell where it would be better to just drop this cell rather than try to draw some kind of conclusion from these 2 cases. So what happens often in practice when you don't take this stratifying kind of perspective is that people fit one additive logistic regression model with one coefficient on income. And implicitly, then we can predict these values in every stratum. And you're really assuming that the curve is really the same for everybody, perhaps with like a little intercept shift because of the other additive predictors. And so this would be a highly structured conclusion. Here you could estimate this curve really precisely, but you'd be losing a ton of information because you have like the assumption that the effect is the same for everybody. And so broadly, what we want is something in between these extremes. We want a balance between the structure of that additive model and the flexibility of the fully interactive model. And so that's what we're going to go for with an ensemble approach. So to take our structured extreme, this is exactly the curve that produced the additive logistic regression on the previous slide. You could have your log odds of college enrollment are a linear additive function of the inputs where you take income with a log transformation. And throughout, we're going to let the slope on log wealth differ by wealth tercile, just to allow like more nonlinearity in log wealth than simply log wealth. And I'm being a little hand wavy here. I've left off some like first order terms. They're all in there in the actual model. This is just for the sake of fitting it on the slide. So if we do that additive logistic regression, then we could summarize the results among those in educational and wealth subgroups. So here we have the subgroups by parents' education and colors representing wealth. And you see in this plot, it looks like pretty much everybody benefits from an increased income. And that's because we assumed that the effect beta in the space of log odds is the same for everybody in the model. This gets me back to the question about visualizing the middle 90% of the curves. So here we fit the regression model on everybody, and then we visualize. And when I said we cut off at the middle 90%, in this case, like this red curve is the middle 90% of treatments among those for whom one parent finished college and wealth is high. But this red curve is not restricted by like subgroups that also consider race, because that's not visualized in the plot. So that's like a slightly technical point about how we're defining this middle 90% in a way that we can still produce plots without losing everybody. Okay, so we have this additive logit. But then we'd like to have more flexibility. So we're going to gain nonlinearity flexibility by allowing a generalized additive model using Simon Wood's MGCV package. And we're going to add specific interactions to that model to allow differences across the subpopulations. We're going to do this with restricted cubic splines that are penalized. So I want to briefly explain what's going on with those. So here's how we would fit the standard logit model. So we've transformed income to a log scale and assumed that the log odds of college enrollment are a linear function of log income. But we might not believe that. So we might take quartiles of the family income distribution and then assume a linear term that's the same through that whole range, but let there be unique cubic terms in each of these sections of the distribution, restricted so that they have a smooth connection at these 3 knots of the empirical distribution of data. And once we do that, we now can relax the nonlinearity assumption. So we actually find when we do that with this package that the log odds of college enrollment increase more slowly and then more quickly as a function of log income. So this change from here to here shows you that we've actually gained something. Like the fit, once we allow nonlinearity, is different from the fit when we have a linear assumption. And now let me just untransform this back to scales that we can interpret more easily. So here we were working with the log odds of college enrollment. We can turn that into the probability of college enrollment by like getting out of the log odds space. And then here I have the x-axis on a log scale, and I'm going to turn that back into a standard dollars scale. And once we do that, we see a result that's easier to interpret than that one I showed you before, where the probability of college enrollment increases at like about the same rate up to near 150,000, and then it kind of flattens out beyond that. And because this is capturing the nonlinearity, this is actually a little bit different from if you just stuck log income as the predictor in the regression model. Any questions clarifying what's going on with the splines?
Ian, just a quick one, if I may. But
yeah,
sort of. So one thing that is sort of nagging in the back of my mind is that why do we create these interactions manually? I mean, why do we care to do this manually, not just use, say, some non-parametric models such as generalized causal random, the generalized random forest that does causal estimation? And I might have a sense for why, and you tell me if that's wrong, or you just tell me why, which is basically that you want to control the terms, the interaction terms that you're creating, which you can't do in the random forest, but perhaps that's not the reason for why you're using.
Yeah, both Jenny and I are pretty excited about generalized random forest. So we have tried that, and we intend to bring it back into the paper at some point, actually, like a tree-based approach here.
Yeah, exactly.
The thing that gets hard with the random forest is that it works great for like, it's making discrete cuts in the distribution and assuming like homogeneous outcomes within the leaves at the end. Yeah. But when the key predictor is continuous, it doesn't always do as well. Because there's some information pooling along a slope that we want to achieve. So we worked a little bit, Friedberg et al. Have a paper on local linear forests where they do a linear regression adjustment within the leaves, and we think that's one promising approach.
Yeah.
And we also think, you might not get smoothness, but you may get something useful from a tree.
Yeah.
Yeah.
Right. Okay. I think I see the reason. Yeah.
So it's a choice we're making, but we're not, we actually like trees and forests a lot ourselves.
Yeah, that makes sense. Okay, so it's not really that you want to control the interactions as such. It's really that you want to maintain some interpolation between the data points.
Mm-hmm.
If I'm gathering your answer correctly.
Yep. And because there's a risk of doing some extrapolation, like on the previous slides, and with a regression, we know with a parametric regression like this, we at least understand what's going on with the extrapolation.
Okay, okay, thank you.
Okay, so before I go on, I'm about to tell you about the causal effect of family income, but on this plot, I have the descriptive association, and I just want to say that that is really big. So if you took people at the bottom of the distribution in this US population, like 20% of them enroll in college by age 20, and at the top, like 80% of them enroll in college by age 20. So as a predictor, family income is enormously consequential for college enrollment. And next, I'll get to results about whether as a cause, it is enormously consequential. Okay, so this is again that linear model we had on the previous slides where things like looked really parallel by assumption. And next I'm going to show you a smooth model with interactions. So here we estimated that generalized additive model where we allowed the smooth to have different slopes within each stratum that's visualized here. So we adjusted additively for race that allowed the curve to have different slopes in each wealth subgroup by education subgroup. And this achieves the flexibility that we want because we now can find differences in the slope patterns, like, oh, it's really steep over here and seems like really flat over here. But we also get some wonky stuff, like really wide confidence intervals over here and this like weird up and down going on that no one really believes among that particular subgroup over there. And so we want something in between these. And this is the reason we're going to go with an ensemble method. So we're going to use many base learners. So each of these is a regression model that we could use to make this plot. So we could make that plot with an additive logit, a logit where income interacts with education, income interacts with wealth, income interacts with race, logit where we have income interacted with education, interacted with wealth, same for race. And then for each of these, instead of assuming that all the continuous predictors enter in log form, we could let them have these smooths where we can have like a nonlinear association that appears from the data. And so we're going to estimate all of those base learners, and then we're going to aggregate them together into one Frankenstein machine learning prediction method. So concretely, we first split our data. We're going to do it in 5-fold cross-validation with 10 replications, but I'm going to illustrate here as though we just had a train test split for simplicity of talking. So we take a learning set, which is in this visualization half the observations, and we estimate the base learners in that learning set. And then we predict from those base learners. So I just showed you, like, I don't actually know how many it is, like a dozen regressions on the previous page. So when we predict, we're going to get for every observation like a dozen different predictions for whether they would enroll in college at their factual family income. So now we have a matrix. Now this matrix of predictions is going to become our predictors in our second ensembling step. So in this second step, we're going to predict the actual outcomes in the holdout set among those using as the predictors the predictions from the first set. So the first set says, how do the predictors relate to the outcome? The second step says, how do the predictions from each base learner relate to the actual outcome? And the result of this second step is going to be a weighted combination of the predictors, a weighted combination of the base learners, which maximizes the prediction of the outcomes in the ensembling set. So that would be like 40% additive logit, 50% some sort of interaction thing, 10% another model. And so then what we're going to do is we're going to now take our observations and make a new data frame of predictors. So in XNew, we've maybe taken incomes and changed them some way to some counterfactual value. And then for those counterfactuals, we're going to predict from all of the base learners, and then we're going to predict from the ensemble to get a new y hat under those counterfactual income values. So in many ways, this is identical to what you could do in OLS. We're just building a predictive model for the outcome given confounders and treatment, changing the treatment and making a new prediction. The complexity here is just that we're estimating lots of base learners and then an ensemble of those base learners. So I should pause here and answer questions about if anyone wants clarification on the ensemble.
So you're basically predicting the potential outcomes, right? Yeah.
Yes.
Yeah.
I mean, we learn on the factual outcomes because that's all we observe.
Exactly.
And then we're going to predict the potential outcomes.
Right. And you use some kind of regularization as well here?
Actually, well, the base learners are regularized when they're the smooth is regularized to not be too wiggly. And And then this ensembling regression is restricted to have all positive weights that sum to 1.
Okay.
So that's not regularized in a sense you would normally think of it, but it does regularize in the sense that you can't get really wild weights because they can't go above 1. And when one base learner gets all the weight, the other base learners have to get none of the weight.
Right. But what do we think about overfitting in this context if we don't use the traditional regularization mechanism?
Oh, yeah. So overfitting, there's a sense in which overfitting we're protected from because we have the base learners estimating in one sample and then the ensembling in another sample.
Yeah.
So if the base learner overfits, it will get 0 weight in the second step because it won't predict for the new observations well.
Sure.
But we are totally guilty of overfitting in the ensemble. And we're comfortable with that because the ensemble is only going to be like a dozen coefficients in several thousand cases.
Okay.
And we feel that that's not too much overfitting to worry about. But yes, there's a limit to our, we haven't completely sample split because we don't want to use up all the cases.
Yeah. Okay. Thank you.
Okay, so here is our ensemble. So we have all these base learner models on the left, and then I have the contribution to the ensemble on the right. And in order to simplify reading this, you see that many of these base learners got approximately 0 weight. So I'm going to change to a plot that only has the non-zero weights. And so here are those non-zero weights. So our resulting model is about half the model that interacts income by race and allows income to have a smooth nonlinear association. We also have about 35% of the model is the standard logit model, where we have income interacted with education, interacted with wealth. And between these, you can see there's sort of 2 choices being made. So in the top, we're basically spending more degrees of freedom on getting a smooth term. And here we're spending more degrees of freedom on getting interactions. And by pooling these, we get like a little bit of a smooth term regularized toward a bit of interactions. And then we have a little weight on these simpler linear models also, which you could think of as a form of regularization, because effectively this means that like the more interacted logit is regularized toward a model that doesn't have the wealth interaction and toward a model that doesn't have the education interaction. Okay, so I'm going to show results because this is actually not that interesting because this is just like this is how we came to our ensemble. But there's not a lot to interpret here, and there is a lot to interpret when we predict those counterfactuals, which is the reason we did the whole process to begin with. Okay, so here's the ensemble results. So I'm predicting here, what we've done is for every person, we predict their outcome under every family income, and then average over the population at each family income value. And so here we're averaging within the subpopulation defined by the facets and the color. And what we see is that when we're predicting college enrollment, enrollment increases really steeply among those for whom neither parent finished college. And it's somewhat in the middle when one parent finished college, and when both parents finished college, this was striking to us just how very flat this curve is. So it really seems that if your parents finished college, there's almost no effect of increasing your family income on whether you yourself will enroll in college. If we turn to the model that has to visualize the results with interactions by parents, education, and race, I guess I skipped over the wealth thing. There's also not a ton with wealth. Similarly steep slope at all wealth values here. Similar here. The one perhaps story about wealth is that when one parent finished college, it appears that income has a bigger effect for those with low wealth than for those with high wealth, which I think also is a story that kind of like heuristically makes sense. When we look at interactions by race, we get almost nothing. So it's surprising to us that the patterns of college enrollment are pretty similar for white, other, Hispanic, and Black once we look within subpopulations defined by parents' education. So our story here really is about heterogeneous effects by parents' education and wealth. Okay, so those were curves, and we are familiar with regression, and we all like regression partly because it gives us point estimates. Like I can say beta equals some value, and that is an estimate of the effect of family income. And so we would like to get to point estimates in this case also. We'd also like to get point estimates that don't extrapolate too far from the observed family incomes. And so to do that, we're going to do three things. So for every person, we're going to predict their probability of college enrollment at their observed income value. Then we're going to take our data frame and add $25,000 to everyone's incomes and make a new prediction for this potential outcome of whether you enroll in college if your family had $25,000 more. Then take the difference between 1 and 2. So for every person, the difference between 1 and 2 is an estimate of the conditional average treatment effect at the observed confounders for that person. And then we're going to take the average over the population, or in subpopulations if we want to look at heterogeneity across the subpopulations. And so when we do this, we see that among the subgroup for whom neither parent finished college, regardless of whether your net worth is low, middle, or high, a $25,000 boost to your family income makes about a 4 percentage point increase in the probability of finishing college. If one parent finished college, then that boost is 4 percentage points if your family has low net worth, 3 percentage points if middle, and 1 percentage point if high. So this just reiterates what you saw in the previous graph, where the effect is higher if neither parent finished college. If one parent finished college, it's high for the low net worth people and smaller for the high net worth people. And if both parents finished college, the effect is like approximately 0. And you see there's no estimate here, and that's because we have fewer than 25 people for whom both parents finished college and they have low net worth, because that's kind of an unusual cell for people to land in. Here I have the results by parents' education, family net worth, and race. And this just again reiterates the claim from the previous slide that once you're looking at interactions by these other variables, there's not a whole lot of interactions going on by race, where we're getting similar effects for all the colors here, once we look within strata of the other variables. So that's it for results. I'll move on to discussion, but maybe I'll pause for just a second if there's any results questions. Okay, on we go. Okay, so we think this is a story of cultural capital and financial capital. So for those with vast cultural capital, like your parents completed college, then you are going to find a way to finish college. And financial capital for you is like relatively inconsequential. And this is why we might find that there is almost no effect to family income among those whose parents completed college. Now, for those with less cultural capital whose parents did not complete college, financial capital helps a bit. So our estimates suggest that if you boost income by $25,000, that would increase college enrollment by about 4 percentage points. And so that's our like substantive takeaway here. I think you could rightly raise the question of like, is this a small effect? So after all, we said like $25,000 is a pretty big income boost, and we think that would translate to about a 4 percentage point increase in college enrollment. So if you were a policymaker looking for an effective way to spend money to improve college enrollment, you might consider a policy approach that would cost a lot. So you could be the policymaker, you could take $625,000 in your budget, and you could hand that to 25 families evenly among this subgroup for whom neither parent finished college. And by doing that, if you take our 4 percentage point increase, that means you would cause 1 additional student to enroll in college. So this would be a cost of about $625,000 for the policy to increase college enrollment by 1 person. And that seems like an expensive policy. In many ways, this reiterates what Susan Mayer argued decades ago, that family income actually has remarkably small effects on children's life chances. And in Mayer's approach, she assumed that the effect was the same for everybody. She did some like differencing econometric strategies. Whereas in our case, we're going to not do those econometric strategies, but allow effects to be different across different subpopulations. But on the whole, in many ways, our results reiterate what she said, which is that other things like cultural capital matter a ton, and financial capital matters some, but it's like limited in its power to change things. So how should we interpret this small effect? We think that small effects are still worthwhile, and we think they're worthwhile for two reasons. So one is that we care for understanding. Like, we did not really engage in this project because we thought the US government was going to suddenly transfer $25,000 to lots of disadvantaged families and increase college enrollment. We want to like understand how society works and understand the degree to which income constrains life chances. And thus we think it's worthwhile to know that income is somewhat important, where if you take a given kid, you had them with $25,000 more, they would have a 4 percentage point higher chance of enrolling in college. And then second, we don't want to be read as arguing against increasing people's incomes, because after all, there are many collateral benefits of income. So if you handed disadvantaged families an extra $25,000, that could be good for many domains of their life. And thus perhaps this would in fact be a good policy, because in addition to a small increase in the probability that the kid enrolls in college, there's like lots of other things that would improve that we might think are worthwhile. So this is the sense in which we think there's a distinction between like policy work and scientific understanding. And our project is really on the scientific understanding side of things, but we think it could help inform some choices about policy. So in a world where effects are small, I think it's worth stepping back and thinking about how we ought to do research in that world, because I actually think that a lot of social science is characterized by many inputs, each of which has a small effect. So in this case, Jenny and I think that when effects are small, it is all the more important to find the subgroups for whom they are larger. And as long as we restrict our attention in sociology to the average effect in the entire population, we might miss important effects that are large in some particular subgroups. And so for this reason, we are really excited about the possibility of doing this with trees and doing this with forests and doing this with methods like targeted learning that explicitly allow heterogeneity across subgroups and search for those subgroups. And this leads into, I'm about to close here, we think broadly scholars of social stratification face a tension where our theories point us to a belief in heterogeneity. We think that in this case, family income should have different effects for people in different family situations. And yet, because we have small samples, it's hard to estimate fully interactive models. And thus we may lean on additive models like those traditional regressions that we see all the time in the literature. And so in this paper, we've taken one middle ground that we don't think is the only middle ground, but we think broadly some middle ground between this theoretical belief and the empirical constraints of research is needed. And so our middle ground here has been that we search for heterogeneity with a flexible model. So this is that base learner with lots of interactions and smooth terms, while we also assume some structure in an additive model so that we can get decent performance when our sample sizes are small. And then in a data-driven way, make a choice that balances between these two extremes. And here that weighted average is like our ensembling approach. So broadly, I'll close with social scientists often study things like this, where we assume a treatment has the same linear effect on the outcome for every subpopulation. And perhaps sometimes we should study them like this, where we explicitly search for nonlinear smooth patterns and allow those patterns to be different across subpopulations. And we would love your feedback on any and all of this, because we are like working on this paper actively. And it's great to get to talk with you about it.
Thank you very much for this